Thank you everybody for attending, and thank you so much to both Hannes and Ezra for the invitation to speak. I'm Charlie, and I will be delivering the first part of this presentation, and Majdi will pick up the second half. And yeah, the topic of this talk is our preprint, amortized sampling with transferable normalizing flows, a collaboration between myself and Majdi, Leon, Saif, Dominique, Michael, Alex, and Kirill. And yeah, please feel free to stop me at any time if you have any questions, anything to clarify. Both myself or Majdi would be happy to answer. And so yeah, I briefly alluded to this in the kind of pre-discussion, but a lot of the groundwork for this paper was laid in a previous work. And so I just wanted to draw attention to a paper from ICML, Scalable Equilibrium Sampling with Sequential Boltzmann Generators. And yeah, so we'll have a brief method section discussing this just because it kind of helps explain the newer paper. And a quick overview of the talk, what we'll be chatting about. I'll start by defining the problem setting. What is the sampling problem? Why is it interesting? And what can it solve? How are we kind of currently solving it? There'll be a section on the necessary background. And then, yeah, as mentioned, we'll cover sequential Boltzmann generators, mostly the method, less results. But then the meat of the method that we're probably interested in is the transferable normalizing flows, because I think this is where the kind of Boltzmann generators really get exciting. And lastly, some experiments. And so yeah, to get stuck straight in, the problem setting. So let's define some preliminaries. I'm just going to see if I can I hide this thing? No, it's okay. Okay, so consider a molecular system of n atoms in three-dimensional space, and we're going to denote the atom positions as x. This is in Rn/3, also calligraphic x. And given this kind of definition of a molecular system, we can define an energy function such that every point cloud or conformation that we get x, we can get a scalar value. And this is telling us some kind of physical behavior or physical properties of that state. It's important to note that in general, x is not permutation invariant. It's not a true point cloud. There's a topology, and this will tell you the atom types of each atom index and the kind of bonding taking place between them. And so the energy function is going to be some approximation of some physical behavior, and that could be varying in complexity from density functional theory, which is quite complex, or down to a classical force field, which is a kind of a sum of various interatomic potentials depending on the atom types and the bonding. And so given this energy function and this system, we can define the following probability distribution known as the Boltzmann distribution. And so this defines the probability of occupying any given state. Here, Kb is the Boltzmann constant, T is the temperature in Kelvin, and intuitively, high energy states are low probability, whereas low energy states are higher probability. And so if you were to simulate the system for a while, you would see low energy states occupied with greater frequency. And this is hard to sample. It's a challenging problem in computational chemistry. And this is due to the kind of high dimensionality of the problem. There'll be several modes, and these will be separated by energy barriers, particularly as the scale of the system grows. In addition to this, the partition function or normalization constant Z will be intractable to integrate and compute for all but the very simplest of systems. And when we refer to equilibrium sampling, we mean getting the samples X distributed according to P of X. And so there are many applications of sampling. I think some of the biggest ones might be observable. Well, these are the most general examples. We can do observable ensemble averages. And so if we want the expectation with respect to the target distribution, and you have any function of interest phi, this is the formula. And this is the kind of exact formula. There will be approximations if we have a kind of sampling algorithm for it. And so examples of what phi could be are the energy itself, which would give you the average energy, or it could be an indicator function, which indicates whether the state, or like microstate X, is part of a macrostate A. And so the distinction between these states is that X is actually a specific conformation, but A is a more general notion of a state. And so you could define this with respect to dihedral angles. You could define this with respect to some kind of RMSD from a specific conformation. Or it could be a kind of, A could be a folded or unfolded state if you have a protein, or perhaps a bound or unbound state if you have a protein ligand system. And so actually, if you were to make phi be this indicator function, you'll get what we call a restricted normalization function constant. And so this would enable you to compute free energy differences, which is perhaps the biggest application of sampling. And Here we have two different states, A and B, so it could be bound and unbound, and we've computed these restricted normalization constants, and this free energy difference will tell you how thermodynamically favorable these states are relative to each other, and can be used to compute things like binding affinities, which are helpful. And so the classical approach to sampling within computational chemistry, at least, is molecular dynamics. And in molecular dynamics, we integrate the equations of classical mechanics with respect to time. And each of these integration steps requires an energy evaluation so that you can kind of, or technically a force evaluation so that you know the forces that are currently acting upon the atoms. And this is fine. And assuming your system is ergodic and that you have simulated for a sufficiently long time period, if you then randomly sample your time index, you then get samples from the Boltzmann distribution. But in practice, this can be kind of intractable to run for a sufficiently long time. And so the main reasons for this are that small time steps are required to limit discretization error. If you're working with proteins, I think 1 femtosecond is quite a common amount. And this means that for every kind of microsecond of simulation time, you're going to have a billion energy evaluations, which is quite costly. And of course, you have, or not of course, but you require long simulation to traverse separated modes. And so as mentioned on the previous slide, in high dimensional, and even high dimensional could just be like a tetrapeptide or octopeptide, the systems can have many modes separated by energy barriers, and this gives rise to the notion of a metastable state. And so as you're simulating with respect to time, you're going to be, your simulation will have a tendency to remain in a low energy basin, and it's less likely to transition between two low energy basins that are separated by an energy barrier. And so you'd say that it is metastable within that region. And so I've got a kind of little marking on the right-hand side. So we have a 5 microsecond reference trajectory and the Tika projection thereof. And then we have a 10 nanosecond kind of baseline trajectory. And we see that actually within those 10 nanoseconds, we haven't left this mode as defined by the Tika projection. And so those two are maybe kind of fundamental limitations of molecular dynamics, but actually another limitation is that molecular dynamics lacks amortization. And so you have to start from scratch for every new system of interest that you come across. And so if we're interested in peptides and I've run a 5 microsecond, go. Okay, I thought that was a question. Sorry.
Yeah, I think just someone accidentally unmuted. All good?
Okay. So if we're interested in peptides and we've simulated 5 microseconds for a certain sequence, if we then mutate one of the residues, we don't really have any specifically useful information for like solving the Boltzmann or sampling from this new Boltzmann distribution defined by the different system. And I think with the interest, or with all of the success that we've seen of generative models, there's a lot of interest in applying generative models towards amortized sampling such that you can have a big and costly pre-training phase and perhaps requiring lots of energy evaluations on systems, kind of a general set of systems, but then actually when you want to sample from a system of interest, it's much more efficient. And so that's kind of the vision of why we want amortized sampling. And yes, so to kind of get into some of the specific background that we'll need to understand the methods, we'll start with finite normalizing flows, often just known as normalizing flows. And these consist of a sequence of differentiable invertible functions that are composed to kind of form a more complex function. And so here we have f theta is the composition of k different functions f. And we train this to map samples from a simple prior to an approximate target distribution, or technically actually you train to map from the target to the like an approximate prior. But x is therefore, if you use the function f theta inverse, because of course if each function f is invertible, we can invert the entire composition. And if we apply this to z, a sample from a Gaussian prior, we then get an approximate target sample x. And then this also induces a distribution q theta of x. And so this push forward density, we can compute the density of, and it's just the sum of the log density of the pullback to the prior and the sum with the log determinant term. And because of the compositional structure of f, if each of the individual f has an easy to evaluate log determinant, the kind of global or composed log determinant is just a summation. And so This means it's tractable to compute. We can train with maximum likelihood. And I think this is the key advantage of normalizing flows, is that you have very fast likelihoods. And here we have a finite number of functions f, but if you were to let this tend to infinity, you would recover a continuous normalizing flow. And so this is normally introduced as considering an ODE where you parameterize a velocity field, u of t. If you want to sample, you can draw a sample from the prior and then simulate the ODE to get an approximate target sample. You can also compute the log density using the change of variables formula, at least the continuous variant of it. But this is quite expensive because it requires the gradient, or no, the integration of the divergence of the vector field. There are some tricks such as Hutchinson's trace, but we found that for the applications we were interested in, this would introduce like an unacceptable amount of error. And in some cases, you actually even want the gradient of the log P1, in which case it's very costly because you have to take the gradient through the ODE solver, which is internally computing the divergence. And yeah, these were originally actually trained by maximum likelihood, but now it's more commonly flow matching due to the kind of it's simulation free and more efficient. And both normalizing flows and continuous normalizing flows are examples of likelihood-based generative models. And one interesting application of these is within Boltzmann generators, in which they are paired with self-normalized importance sampling. And so if we have our target Boltzmann density P of x, and also the density from a learned normalizing flow, Q of theta. If we then generate, I think n samples, xi up to n from Q of theta, for each sample, we can compute the importance weights, which is simply the ratio of the target density and the proposal density. It's worth noting that whilst P of x is difficult to sample from, it's trivial, or we can assume it to be trivial to compute the energy if we need to. And given these importance weights, we could then perform multinomial resampling to get an approximation to the Boltzmann distribution, or we could use this equation on the left to do an approximation of an observable. Question, please go.
Why does being able to evaluate the energy function mean that you can compute Wi, where you, in your equation here, need P of x?
Oh, so sorry, so if we have a likelihood-based generative model, we can get Q theta x. And I'm just mentioning that P of x, it's easy to generate or calculate the, actually, technically, there's a caveat of it's the unnormalized density. Maybe that's a notational error, but it's trivial to compute the unnormalized density P of x, which is what you need for self-normalized importance sampling. But it's difficult to generate the samples from P of x, if that clarifies the question.
Yeah.
And actually, Q of theta can be an arbitrary proposal, but if the overlap or if there's a big distributional mismatch between Q of theta and P of x, the weight variance will blow up and it's just going to be completely intractable. And it's not, whilst theoretically infinite samples from a Gaussian as your Q theta would be fine, it's in practice not going to work very well. And
so in this slide, I think in practice, what will happen is it that we have our unnormalized density at the top here, and then you have your Wi, you have your sum over your Wj, and you can pull out the Z for both, and then your Wi divided by the sum of the Wj. Yeah, your Z's will cancel out.
Exactly. Yeah, it's just a way of self-normalizing with respect to the sum of the weights. Okay, and to give some kind of visual intuition for the Boltzmann generator, there's this nice figure from the original paper by Frank No et al. And you sample a Gaussian distribution in kind of frame 1, and then in frame 2, you've mapped this to your proposal distribution using, in this case, they were using normalizing flows. You then evaluate the likelihoods, Q theta of x for each sample, and this enables you to reweight and do multinomial resampling, SNIS. And this gives you consistent or asymptotically biased or asymptotically unbiased samples from the target Boltzmann distribution. Things to note is that actually in the Boltzmann generator, you need samples P of x to train the proposal itself. And so in the original formulation, this would have been a molecular dynamics trajectory. And also the error in the proposal can arise both from bias in the training data of your generative model. So perhaps one mode is overrepresented, or it can arise from kind of model expressivity issues of the model actually not being able to model the distribution well enough. And so the requirement of samples from P of X is quite a big limitation for the standard Boltzmann generator. If we're trying to achieve amortization of sampling, and that's either going to mean faster wall time or fewer energy evaluations than molecular dynamics, if the first step of the method is to actually run molecular dynamics and then train a generative model on the system of interest, evidently it's going to be pretty challenging to actually see any wall time or energy evaluation speed up. And so this kind of leads into the next paper, which is I think, a really interesting one by Leon and Frank No again. And this is the transferable Boltzmann generator. And so they were using a continuous normalizing flow for proposal generation. I think that's the direction Boltzmann generators had been heading in due to the higher expressivity, and I think flow matching kind of enabled this. But it is worth kind of I'll keep coming back to this point, but generating the likelihoods of the samples is incredibly costly due to the integration of the divergence. And so actually, I think it was on the order of about 30 times slower is what Leon found. And so that can be quite costly. But what they do in this work is they also condition on these conditional features. And these features are the atom type, the residue type that the atom belongs to, and the residue position in the sequence. And then they parameterize this with an equivariant GNN. And they then pre-train using flow matching on a large set of training systems. And after this pre-training phase, because the velocity field is conditional on the conditioning vector, you can actually then generate samples by integrating and self-normalized importance sampling on completely unseen systems by just passing in a new conditioning vector that hadn't previously been seen. And so this is a massive advantage towards the goal of actually achieving amortization. And they were able to demonstrate this on systems up to dipeptides, which range from about 20 to 50 atoms. Yep. Okay. And the final bit of background that I'll cover is the TarFlow, which is a relatively recent. It came out, I think the preprint came out in December. It's a new normalizing flow, and it was originally applied in the image domain. I think this paper is super exciting, and I think it was the first example, I think, of a normalizing flow that was really performant at modeling ImageNet, like a pretty complex image distribution. And so TarFlow is a blockwise masked autoregressive flow. Fundamentally, it is a causal vision transformer. And so you take the image and you split it up into patches as you would in a vision transformer. And this gives you a sequence. And you then, kind of either generation or in the other pass, each kind of block, it performs a pass by performing a transformation to the sequence. And so as we can see, actually, if we look at this equation, the first index I, if I equals 0, you don't actually update the first item in the sequence. But then for every successive patch in the sequence, you perform an affine update where the scale and the offset is parameterized by a transformer. But crucially, this is also causal. And so you're only able to look backwards in the sequence. And the combination of this causal and affine update with the first one moving means this transformation. Oh, Hannes hit me with the question.
The purpose of the raised hand is so you can continue until you think a good question. It's a good time to take a question. But then now is a good time. So I understand if we have an or element-wise, or let's say dimension-wise, autoregressive model, how then it leads to an easy to compute Jacobian. Also, if we only update our parameters with a scale and a shift, then it's easy to see how we have an easy to compute Jacobian. Now we here have a sort of mix of these two. Is that right? We still only update parameters with a scale and a shift, but it is parameterized by all the previous outputs that our model, or all the previous shifts and scales that our model already produced for the other patches.
Mm-hmm. Okay. Or actually, it's yeah, in a sense, because you perform the affine update, and then after the affine update, that's the kind of input. And so, of course, to update the first token, you don't need to know anything about the prior sequence. And then when you get to the second token, you'll know, or that the first with using the index. You then only need to pass in the unmodified previous one, and you can then recover the affine parameters and then invert the function. So I think the causality and affineness is necessary for the invertibility, such that you
Okay,
can do
so
it.
the Jacobians of the individual patches are easy to compute because it is a like real NVP type update where we have only shift and scale. And the Jacobian of the overall image is easy to compute because we combine patch updates in an autoregressive manner.
Yeah, but actually the compute the log determinant, I mean, yeah, it's just summing over the scaling, like a kind of real NVP style.
Yeah.
And yes. Okay. And one thing though that we'll notice is that actually you haven't updated at all the first item in the sequence, and you're only operating causally, and so you must permute. And so by permute, I mean before you do this whole kind of causal affine update, you change the sequence ordering. And in the original TarFlow paper, they simply did an identity and a flip, which corresponds to kind of I believe row-wise top left to bottom right to like the inverse, and that was sufficient for images, but it's something we worked on in the new paper. And this enables kind of you to compute a kind of more like just a general function without this kind of causal restriction. Yes, okay. Now on to sequential Boltzmann generators, which was the preceding paper. Just to kind of do an overview of the contributions, slightly confusingly, but the prior state of the art. So in the sequential Boltzmann generators paper, we were only considering single systems. So you have an MD trajectory for the system you care about, and you train a generative model on it, and then that is your proposal. But the prior state of the art was actually from the transferable Boltzmann generators paper. They had a few single system experiments in there too. So compared to the prior state of the art, we replaced the continuous normalizing flow with the finite normalizing flow. And this was essentially just the TarFlow. Instead of operating on patches of images, we were just operating on a sequence of atoms. And so this was very much like the ability to do this was very much a big part of the paper. Instead of using enforced equivariance, we just do soft equivariance data augmentations. This is kind of following the direction that some of the bigger protein generative models have been heading in. And we are able, by doing this, to do not only self-normalized importance sampling, but more sophisticated sampling algorithms that require more energy evaluation, such as sequential Monte Carlo. And so, as I've previously mentioned, it's quite costly to get the likelihoods from the Q theta x of a sample from a continuous normalizing flow. But for the normalizing flow, it's much faster, and this means we can try some more sophisticated algorithms. I think, I'll take the question.
Yep. Then that's or like here the distinction that's not the clearest to me is SNIS versus SMC. Does the do we now still just draw independent samples from your normalizing flow, or do we use your normalizing flow after it's trained to construct some Markov chain and use those samples?
It's the latter. There's actually a
Okay,
slide on this, so we will go through a bit more detail, which hopefully will clarify any of that.
sounds good.
And yep, and kind of experimentally, what did this mean? In the prior state of the art, they were just doing dipeptides, but by making these changes, we were able to quite accurately sample up to hexapeptide systems. And yep, I will move quite quickly through this, but soft equivariance, we just use a standard Gaussian prior. We rotate the training data. One thing which is perhaps interesting is that if all of the training data is centered and we are training from a standard Gaussian prior, you end up with an issue of degeneracy and that you're trying to map a higher dimensional space into a lower dimensional space. And so we add a center of mass, some noise to the centroid. I think this also has a regularizing effect, which for the small single systems, given a very large capacity transformer, I think was actually desirable. But in doing so, actually, because the training data had this center of mass distribution and I mean, actually, just to clarify, the training data is centered on the origin center of mass until we add this. And so we know exactly what the centroid distribution is. It's this Gaussian. Because it was applied to the training data, the proposal distribution is also going to have the same or approximately the same distribution over the centroid. So we're going to generate things that are not at the origin. But the target is invariant to the centroid norm. It doesn't care where it is. And so when we perform reweighting or self-normalized importance sampling, actually the distance from the origin of the proposal sample will change the importance weight, which is undesirable. But we know that the centroid norm will follow a scaled chi distribution of 3 degrees of freedom. And this is done in log space, but it's slightly more intuitive in the non-log space. If you just remember the equation P of x over Q theta of x, we're effectively just dividing out the effect of the center of mass chi distribution of 3 degrees of freedom. And under some assumptions, you can prove that actually the effective sample size, which is kind of the variance of the weights, is improved by doing this. Yeah, and there's a proof for that in the paper. And so,
okay, so I can see how we can do this, but why is it necessary? Like you said, this with different dimensions.
I think, well, the dimensions issue is more a question of training. It never worked well, but I think mathematically you end up with an issue of degeneracy of trying to map things to a kind of like a lower dimensional space. But then in a practical sense, what effectively, yeah, the intuition here is that actually what can happen is if you imagine the importance weight of a single sample, you can imagine that like a low energy sample, so a nice sample will be generated by the proposal, but it might be generated very far from the origin. And so your model is then going to say, this isn't very likely, it's because it's far from the origin. But when you compute the importance weights, it's going to have a very low Q theta of x, but like also low P of x, and this will lead to you having a very large importance weight. So does that make sense?
So that's talking about the correction that's applied and not why it is necessary to add the noise in the first place. So to my understanding, we have our Gaussian samples. The Gaussian samples are not necessarily zero-centered, right? And our conformers, they are zero-centered. So there's a difference in the degrees of freedom that our data and our prior has. So why wouldn't we just zero center our Gaussian noise instead of adding Gaussian noise to our zero centered data?
Yeah, I mean, it's a good question. I think you could even like another approach would be you can take out one of the atoms and just kind of operate on the smaller degrees of freedom. This design choice was actually it was experimentally motivated. I mean, we did try training with the mean free prior. We did try like on the centered data, and we just found that it worked better to train with a normal Gaussian prior and with because you can actually match the centroid the noise that you're adding such that it exactly matches the system, and so the kind of centroid distribution doesn't change between the prior and the target. But yeah, so it was experimentally motivated, although admittedly we didn't explore the possibility experimentally of just operating on one fewer atom, which would be another valid approach. But yeah, that's how we kind of made this design choice.
Yeah, that would be a bit weird. But okay, so do you have numbers on the zero-centered prior versus the Gaussian center of mass data?
I do not. We don't have like the experiments, but it was yeah, it was a much more stable training procedure with the
okay.
I think, I mean, one thing that maybe we didn't revisit it in the new paper, but one thing that's worth remembering is that these systems are pretty small. You might have on alanine dipeptide, it's what, 22 atoms, and you might have 100,000 samples, and it's hard. We didn't fully untangle how much the regularization was. Perhaps there's a regularizing effect that's actually helpful, but at least experimentally we found it helped, and we kind of post intuitions that actually it's bad to have.
Cool.
Okay, and so yeah, coming to sequential Monte Carlo, we had the little question. So in sequential Monte Carlo, we actually did a continuous time variant of SMC. There are kind of other variants that Majdi will touch upon, but you define an interpolation in log density, and if this has a time parameter tau, and so when tau equals 0, we have exactly the proposal density or log density. We have log q theta when tau equals 0, and when tau equals 1, we have exactly the target. And this gives you a smooth interpolation between the two densities, like so. And in SMC, you're able to propagate the samples and track their corresponding weights. And so you perform Langevin dynamics, which is this, with this coupled SDE-ODE system, with the DXT, you're performing a step of Langevin dynamics with respect to your energy interpolation, the time varying one. You kind of step time forwards, perform Langevin, and you can also update the log weights using this d log WT equation. And if you were to just run from time equals 0 to time equals 1 without doing any resampling, you would recover annealed importance sampling and then just do the reweighting at the end. And if you were to do it, if you have resampling within the time period, it's sequential Monte Carlo. And often you use what's called adaptive resampling. And so there'll be some triggering cutoff of the variance of the weights, and then you kind of trigger resampling and reset the weights to be uniform again. And to give some kind of intuition, there's this really nice illustration from Arnaud Doucet and co-author's book. And so if you start with initial samples of uniform weights, you then propagate the samples and the weights. And so it's a little hard to see, but the samples have been propagated in the fact that they've moved to the left or the right. But it's very easy to see that the weights themselves have changed. So whilst all the dots were the same size, they're now different sizes. You then resample, and effectively this just means that the bigger weight samples are likely to have multiple copies made. And then if you propagate in a stochastic way, you can see that the 3 points in the same place have propagated to different places, and you've updated the log weights, and this kind of procedure proceeds. And so under some conditions, this is like a lower variance estimator. But I think the intuition I really used to motivate why you'd want to use sequential Monte Carlo is, let's say your proposal distribution doesn't have a good overlap with your target density. Maybe all of the samples are too high energy. They don't have the fine grained detailed correct. This is actually a very powerful way to kind of, you're not only reweighting single shot with SNIS, because if you don't have any good samples, you can't, SNIS doesn't help you. But with SMC, you are actually able to anneal towards the target distribution, and you can refine the samples in that way. And yep. And so one very final point before I pass to Majdi is that at every step here, we need the gradient of log PT, and log PT is includes log Q theta. And so this is where I mentioned earlier that if you're using a CNF, it's going to be very intractable because you're going to have to take the gradient of the simulation of your divergence, and that is going to be too costly to be really practical. So that was essentially using the normalizing flow. It was a twofold thing of the normalizing flow was sufficiently expressive to model the molecular systems, but it also came with really, really fast likelihoods, which kind of opened up lots of other sampling algorithms. I'm now going to pass over to Majdi. I think I'm going to stop sharing. Oh, please go.
Yeah, do you know the flow and yield importance sample bootstrap paper?
Flow and yield importance. Is that the FAB paper? Flow and yield bootstrap.
Yes.
Yeah.
Yep.
Yeah, and you could.
So,
okay, go.
What is the difference between your SMC and the AIS that we do here? Is it that this is like a parallel sample procedure where we are not just propagating or generating a single weighted sample, but we have like a particle method where we are reweighting multiple particles at the same time?
I mean, I think there's this distinction between just like AI. It's not with the difference with Fab isn't just that whether you're resampling or not. I think if my understanding is correct, Fab is it's essentially using AIS within an objective, and so it's kind of a different objective to train a normalizing flow without having necessarily the right data. Whereas
it's doing that on top of this. So it's then training with this objective in a aim to get better weights for this resampling procedure.
Yeah, and so in this case, in the SMC, we're using the normalizing flow is completely static when you start using it. There's no once the weights are trained, nothing happens beyond that.
But now about the correction procedure after you drew samples from your normalizing flow. Like you have AIS, which Fab is doing, and you have this particle method here. So is the, yeah, okay, I guess the main difference is that here we're, like the particles depend on each other during the reweighting procedure.
Yes,
if you want
I
me
think
to, so AIS, if you're talking about the difference between AIS and SMC, AIS essentially we just don't do this resampling procedure. So we just keep accumulating the weights on the particles towards the very end. If that's...
Okay, I don't want some SMC people to shout at us now. Maybe they would say AIS is AIS is, or SMC is a more general version than AIS. And you can't say the difference between AIS and SMC is XYZ, or like in the difference that you, the difference between Fab and what you guys are doing. I think I don't know the terminology. My assumption would have been that SMC is a, let's say, super category of AIS.
I think that's a commonly held view.
Okay, but independent of making SMC people angry, the main difference here between Fab and your paper is now that the reweighting depends on the or uses all particles, and the particles depend on each other.
But also, like we don't do any kind of changes to the objective because they have
which would be nice, right? If we could also do that here for your reweighting procedure.
No, for sure. I do actually think that it would be quite, we didn't evaluate it in the transferable paper. We did a few different algorithms, but Fab would be a perfectly valid algorithm to have evaluated alongside the others. I'm just going to switch the screen to Majdi so he can present his part.
I just need screen sharing permissions. Okay, got it.
If someone in the chat feels like putting some Wikipedia quotes in here on SMC and AIS, or so we get the terminology correct, then feel free to do that. Or Charlie, if you feel like doing the lookup while Majdi is talking.
Yeah. Okay, cool. Can you guys see my screen?
Yep.
Okay, great. So now we kind of like will transition to the main methods from the transferable normalizing flow paper. And so naturally, and we kind of alluded to this in your discussion earlier with Charlie, that sequential Boltzmann generators kind of demonstrated that we can have really good normalizing flows, give a good proposal, and that they can scale to larger peptide systems, but it was still done on single systems. And now we naturally have the question of, can we extend this to transfer across peptide systems, like across scale, across size, across different systems. So naturally, so here we give an overview of the transferable normalizing flow, which we dub as Prose. And similarly, as done in the transferable Boltzmann generator by Leon, we just condition we add conditional features based on the peptide system. So this includes atom types, residue types, the position of the residue on the sequence and the sequence length. And so if we have like a trained normalizing flow, what inference would look like is that essentially we'd sample samples from a Gaussian, and then condition and pass in these conditional features into these autoregressive flow blocks where we apply some permutation. So here we have some chemistry aware permutations that I will describe in the following slide. But essentially we would permute these atoms, we pass it into this transformer architecture, which will provide us these offset and scale values that we saw earlier and perform some affine transformation. And then when we undo this permutation and we repeat this t number of times to result in a sample from our approximated distribution. And how we train this model is that we've generated a data set of varying peptide systems across sequence lengths from dipeptides to octapeptides, and we generate these trajectories, and we train this model via maximum likelihood. And so to kind of tell you guys a bit more about the chemistry of permutations. So in
sorry.
Yeah.
You train with maximum likelihood?
Yeah, or you just, yeah.
Then how?
So given samples from your data, like ND data, we do
you train on ND data. Okay.
Yeah.
All right, then what is your, or will you later talk about what is the training data?
Yeah, we will talk about this in the experiment section. So I'm just kind of now alluding to it, but
yeah.
And so the chemistry of word permutation. So in the original TarFlow paper, in the image setting, they only provide like 2 permutations, identity and identity flip on the image patches. And this was kind of like sufficient for the modeling task. And in the sequential Boltzmann generated paper, they use these same permutations, but this but the atom ordering is provided by the PDB file. So they kind of have these atom orderings given residue by residue, and they do an identity and identity flip in order to have all these atoms kind of attend to each other throughout the transformations. But naturally, it may be that this might be suboptimal if it's only used on its own. And naturally, we have a lot of information from the topology, and the transformer could benefit from having diverse permutations. And so we propose to interleave this residue by residue permutation with these backbone first permutations. So the idea is that we just take the backbone atoms from each residue, generate or update the coordinates of these atoms first, and then update everything that's like not part of the backbone, like side chains. And this is great in the sense that if you think about if we've autoregressively already generated the backbone, then the updates to the side chains are influenced by the global structure that's determined from the backbone. So like in the transformer, all the atoms from the side chains will attend to the previously generated backbone atoms. And of course, then we also have the flip of this. And then also furthermore, we kind of modify the transformer architecture. So in sequential Boltzmann generators and TarFlow, they simply just, when they have conditioning information, they just do additive conditioning. But inspired by the protein transformers that we see in recent works like AlphaFold 3 and Proteina, we leverage the conditioning information within these like adaptive layer norms and transition box instead. And we see, like we have ablation studies in the paper that we see a performance gain using this over additive conditioning. And then lastly, so in the paper, we evaluate Prose on a variety of sampling algorithms like we see in self-normalized importance sampling and SMC, but we also investigate a procedure that we call self-refinement, where say, given like some pre-trained normalizing flow on data, we want to do this method of like iteratively improving the model. So like first we generate samples from this pre-trained normalizing flow. Then we re-weight these samples to be consistent with the target Boltzmann. And then we feed these samples back into the normalizing flow to update its parameters. And we kind of do this in a iterative cycle. And this is kind of actually like, I mean, it's been briefly talked about in the original Boltzmann generated paper, but also you kind of see this in sampling based papers where they generate samples via some either SDE or whatnot, and then they train on these samples that they've generated. So we kind of do this, but this is assuming a pre-trained normalizing flow. And so yeah, so now we kind of transition to the experiments, which we'll just talk about the many peptides MD data set that we've generated and the experimental setup and all the experiments that we've ran. So we've generated, so here's many peptides MD. It's a data set consisting of about roughly 22,000 randomly generated peptide sequences that we simulated for 200 nanoseconds. And so this is kind of like some statistics on the number of systems per sequence length. And then for the evaluation, we've generated for dipeptides, tetrapeptides, and octopeptides, 30 systems, each simulated for 5 microseconds. And furthermore, like we do this like random generation of sequence in order to, we were prioritizing coverage of chemical space over I guess, yeah, just prioritizing coverage of the chemical space. And so, furthermore, we like make this data set publicly available through Hugging Face, and we provide like the full trajectories, which kind of amounts to like 10 plus terabytes of data. But we make this available in a like a streamable web data set format, which makes it easy to use and adopt. And yeah, so yeah, this is publicly available for people to kind of leverage and use and build off on. And so given this like many peptides MD data set, given the model that's trained on the 200 nanosecond trajectories, we evaluate on unseen peptide systems for these dipeptides, tetrapeptides, and octopeptides. And we compare the samples to the reference MD from that was simulated for 5 microseconds. And moreover, we report the effective sample size and the Westerstein 2 distances on energy, dihedral angles, and Tika projections. So the idea is that the energy will capture is like sensitive to fine grain details. So this kind of promotes model to get the fine grain details correct, whereas the dihedral angles and Tika projections capture macro level detail. And if you can kind of think of that, like these metrics altogether, kind of give a complete picture of the performance of a generative model, right? So like you could have in one case where the energy W2 could be pretty good, like the model is able to match the energy distribution pretty well, but it could be completely missing one of the macro states. Or in the other case, you can be able to sample from all the macro states, but get the fine grain details incorrect, leading to like a high energy W2. So like it's important to emphasize that we can't like look at each of these metrics individually, but we can, but as a whole, we can kind of correctly assess these models. So like to kind of give like a visual intuition, like here we see like this is the energy distribution plots between some MD and the proposal, and then the proposal after reweighting. And the Tika metrics between a reference MD and let's say our generative model with self-normalized importance sampling, and one set of dihedral angles from also comparing the reference MD to Prose. And so like you can see that if there are cases where you can have the energy distributions be pretty well matched, but be completely missing modes from your generative sample, like generative model, and vice versa. And so yeah, and then this was generated for an octopeptide system, so this is quite nice. Moreover, on this slide we show a GIF of comparing like MD to our generated samples. So here we have samples gathered from molecular dynamics that was run for 5 microseconds, or like 1 billion energy evaluations. And here we have like a frame by frame comparison of MD and our Prose with resampling. And this was done up to 10 million energy evaluations. So I think like in MD, this would be simulated for 10 nanoseconds, I think. Or something roughly like this. My conversions might be off. But the thing to note is that here we see that MD gets stuck in one mode. And so this really highlights the case of where Prose with resampling is able to cover all the modes much more efficiently than MD would. And here are some like numerical results. So given like a fixed budget of 10K energy evaluations, we evaluate all these different models like ECNF, which takes the transferable Boltzmann generator model weights that was trained on dipeptides, and we just evaluate it on these on our evaluation data set. We train an ECNF using the training recipe outlined in the sequential Boltzmann generator. And this ECNF is trained on dipeptides and tetrapeptides, and we evaluate it. And we evaluate the standard TarFlow. So this uses like the additive conditioning and just the normal transformer architecture. And Prose has these modifications to the architecture plus chemistry-aware permutations. We could see also that ECNF, like we were not able to train or sample from octopeptides because it was just too costly. It takes about 14 GPU days to sample per system. Thus, like this emphasizes the need for like fast likelihood estimations as system sizes grow. And we can also see that Prose overall performs pretty well across all system sizes. And it's kind of like to our knowledge, the first example of like transfer across scale, like scale of sequence lengths and across different systems at this magnitude. Moreover, we show the performance with respect to like energy evaluations. So here we do like a study where we see that Prose is the most performant across all energy evaluation budgets. And this is actually evaluated for 30 tetrapeptide systems where we simulated all of them for 5 microseconds. And we can see that like, and this is all for a fixed compute budget. We do have like this baseline MD that we show in purple is just a shorter MD trajectory. And we compare like, so not to be confused with the reference MD trajectory. Which we use as our ground truth. And then we can also see that like despite the MD towards the end being very closely matched in energy W2 at higher compute like energy evaluations, it is still there's still quite a big gap in the TICA metric. So essentially suggesting that MD has not sampled from all the metastable states. So if you think back to the GIF we showed earlier, here we see that MD is able to get the energy well towards the end, but it's still not able to cover from all the metastable states. And here we also see that we were not able to evaluate ECNF for larger energy evaluations due to the prohibitive cost of to compute the likelihoods from it. Moreover, we look at the flip side where we, instead of looking at energy evaluations, we look at the performance with respect to wall time. So here we see we have MD in the purple, ECNF in the red, and the darker purple is Prose. And actually even like MD performs very, very well for energy W2 at a much faster than Prose does, right? It's more efficient in this in the case of energy, but still we see this big gap on the TICA metric. Again, so we're just re-emphasizing essentially like looking at these metrics as a whole rather than like products of each other rather than just individually. And also I'd like to also further emphasize like this MD was run with a cheap energy function, right? We just do the amber force fields. And you can imagine if you were wanting to use a much more costly energy approximation, like for example, from density functional theory, the Prose would be more efficient if you think back to the energy evaluation plots that I showed earlier. That's just more performant per energy evaluation. So if the energy evaluations were to be more costly, MD would be would likely be less performant with respect to time. And then lastly, we investigate Prose as a good proposal. So we have seen that Prose is a pretty strong, gives a pretty strong proposal, and we are investigating all the different sampling algorithms accordingly. So we compare like self-normalized importance sampling to different SMC variants. So we have the continuous time SMC that Charlie presented, but we also have like a discrete time version, which is essentially, you can kind of think, if I were to like summarize it really quickly, it's like doing SMC with like unadjusted longevin for continuous, and then doing SMC with like metropolis adjusted, because we're able to discretize time, and then we can get, we just need a kernel that can satisfy the detailed balance equation, and this kind of removes discretization error. But what's really interesting to see is that SNIS is like pretty competitive in performance to like the more sophisticated SMC methods, like which suggests that we have pretty sufficient overlap in the proposal, and that yeah, so we have pretty sufficient overlap in the proposal. And moreover, what's really interesting is that we see the SNIS with self-refinement as a suitable alternative to these annealing-based methods, where in the tetrapeptide system, we see consistent performance gains, or overall performance gain, given this constrained energy budget of 100,000 energy evaluations. And then lastly, we investigate the case of generalizing across temperature. So kind of like the experiment setup is that we've collected MD for, we collect samples from MD ran for 1 microsecond at higher temps for a single tetrapeptide system. And we are, and without training on these tetrapeptides, on these collected MD data, we're looking to compare, if we do Prose with self-normalized importance sampling to these target temperature, if we have 2 cases. We either scale the Gaussian prior, or we just like sample the Gaussian like as is. So how do we scale the Gaussian prior? Is we just take the, we scale the Gaussian to the inverse temperature beta, and then we just pass these into the normalizing flow and gather samples from it. And what we could see is that the on the energy W2 and the Tika metric, that the by scaling just only the prior, we're able to generalize across temperature, which is really interesting, actually. And this, I want to emphasize that this is like, we're not retraining the model or like doing any fine tuning. So this is kind of just done at inference. So, and then with that, that kind of concludes the experiments. And so to summarize, like the overall talk is essentially we have Prose is a transferable normalizing flow that can generate samples for like arbitrary peptide sequences across different systems and across scale, like the sequence length. We also do a rigorous study of like the energy evaluations and wall-time efficiency gains over, like we demonstrate this over molecular dynamics, suggesting that like we learn a pretty good amortized like sampler. And then Prose itself is actually pretty suitable for any like a variety of sampling algorithms, and we even see that this procedure of just training on the samples you generate, like self-refining yourself, gets the best performance on tetrapeptides. And lastly, we provide many peptides MD. It's like a public data set for people to use and building on this work, hopefully. So yeah, and here I'll just keep the links. So we have the links to the code, the data set, and the model weights. And yeah, if you guys have any questions, I'm happy to take them. I'll keep these on the slide in the meantime.
Okay, thanks a lot. So I would just have some simple questions, like now, this TarFlow, how much, or do you perform any patching, so to say, like happening in TarFlow?
No, so we do generate the atoms like one by one, but you could think of maybe like patching as in like generating things like residue by residue, right? So
your so your TarFlow is just an autoregressive normalizing flow.
Yeah, pretty much just on the atoms. Yeah.
Interesting how naming changes and evolve. Now, TarFlow gets credit for this having autoregressive normalizing flow.
Yeah.
Okay. Yeah. But you have these permutations between layers, meaning we see many possible orderings of the atoms.
Mm-hmm. Yeah, and so we kind of, you have the orderings that might come from the P2B file, but also like, I guess this backbone first would also really help in kind of having a more consistent ordering that isn't dependent on your input file. Yeah.
Wait, so you put all the backbone atoms first, and then the sidechain atoms come, or you have backbone sidechain, backbone sidechain?
We interleave between these two. So if you can imagine, like each transformation block might have a different permutation. So the first one might be residue by residue, and then the second one might be the flip of that, and then the other one might be backbone. Yeah.
That's didn't pay enough attention in your permutation section. Okay. One thing in the chat. When you say generalizing on arbitrary length of peptides, did you train on all possible lengths of peptides? Have you tried training on length n peptide and try on length n+1, n+2 peptides?
Yeah, we don't have these results in the paper yet, but we have tried doing this for like training only up to octapeptide and evaluating it on nanopeptide, like sequence length 9 and then sequence length 10 like Chick-Nolan. Yeah, we're hoping to update the script, the manuscript soon in the future with these results.
In that situation, how do you decide whether what you're sampling is good enough? I mean, now you look at some Wasserstein distance and it's like, okay, that's a number. How do you decide that this is a useful sampler for Chick-Nolan, for example? Do you compare with the Chick-Nolan MD data or how?
Yeah. We have some reference MD data for Chick-Nolan.
Okay.
So
I think
additional baselines that are being added in the addition, we have some other baselines which we didn't have in the current results, but for Chick-Nolan there are some other methods you can compare to as well. So yeah,
that's what I don't care about, right? The other method then has another number, and then I also don't know what to do with the delta between those two numbers. Just trying to get an intuition of would we now be able to do something useful with Chick-Nolan? But then are there any last things that you guys want to say before we call it a day?
So no, for me, I mean, it's really exciting work, and we hope like the data sets and the code kind of really hopes to push the boundaries, right, as we try to scale to larger and larger systems, hopefully into more practical cases, right, like being actually useful for real world applications, right? So I think this is just kind of like a step towards that.
Yep. I agree with this being exciting work, and then I would maybe end it here and say thanks to you both for joining, for presenting, for answering the questions, and hope to maybe see you two as well in some reading groups. And to everyone else, see you next week.
Yeah, thank you for hosting, and it's been a pleasure. All right. Take care, guys.
Thank you, everyone. Thanks for coming, and thanks for having us, Hannes.
See you, Charlie. See you, Majdi.